Hello, everybody, and welcome to the virtual seminar series on Gaussian processes, spatiotemporal modeling, and decision-making systems. And I'm really excited to have everybody here. Thanks so much for joining us. My name's Alex Trenin, and I'm going to be one of the organizers who's going to be hosting today's talk. I just want to give a shout out to my fellow organizers, Jeff Pleiss, Yi Wang, and Lisa Simonova for sort of all of their work in making the seminar series happen. And so before we begin, I'll make just a few organizational announcements. The first is that and you can check them out by going to our website, which is gp-seminar-series.github.io. And on that page, you can see the sort of all the previous talks together with the links for the YouTube videos. So check it out. You can also sign up for our mailing list, which sort of will allow you to receive Zoom links for future seminars. And the instructions for that are on the website. So check it out. Seminars typically take place at 1600 UTC. And if you're joining us via Zoom, then you can sort of use the Zoom raise your hand feature to potentially ask questions for the speaker, or you can type your questions into chat. And then the speaker can sort of choose, depending on their preferences, to pause and take questions or to hold questions until later, depending on what they prefer. With all of this said, it's a pleasure for me to introduce Silvia Sellán, who is a PhD student at the University of Toronto and will give today's seminar. Silvia, take it away. The floor is yours.
Thanks, Alex. Yeah, thank you so much for the introduction and for inviting me. My PhD is in computer graphics, or the PhD I'm working on is in computer graphics. So I don't usually get to talk to a more mathy theory audience. So this is a bit of a first for me. So instead of jumping straight to my work with Gaussian processes that I've done in the past few months, I thought maybe it would be interesting for you if I started by introducing you the field that I've been working on and the work that I've been doing for my PhD. And then at the end, I will go into depth into my more recent project involving Gaussian processes and hopefully get all of used feedback about it. So broadly, the field that ties my work together is geometry, how to capture shapes, how to store them, how to study them, how to transform them. So these are some of the types of fundamental geometric problems that I have looked at in my research. For example, consider this project that I worked on with Noam Eigerman from Adobe Research and Alec Jacobson, my PhD advisor in Toronto, that tackles this question. Imagine there's an object, a geometric object like this dumbbell, and it's moving, whoops, spoiler alert, it's moving through space following a trajectory. Now, a very challenging geometric question is, what is the region of space that is covered by the object as it moves? And this is called the swept volume of the shape. In this work, we propose a way of computing it that is better and faster than previous work. Now, the reason that Adobe was interested in this is that if you think about it, this swept volume operation is what you need to compute to do 3D drawing. So using a brush in virtual reality, for example. Turns out our method was actually very robust and it works for very complex shapes. So it can also be used for things like collision detection. So if you have a spaceship that's following a trajectory, you can compute its swept volume along the trajectory and then test whether that swept volume intersects with any other objects to see if the spaceship will collide with an obstacle or not. Or you can swap a spaceship for a car or something like that. So that's one example of what I call a fundamental geometric problem, in the sense that the input is a geometry in the form of an object and a one-dimensional trajectory, and the output is another geometry, and we use mathematical geometric tools to go from one to the other. That's what I call a fundamental geometric problem, and I've worked on others like that. So, for example, I thought I'd tell you about this project with Jacob Kesting, Yanxing Ang, and my advisor Alec Jacobson. What we did in this project was devise a way of smoothing a shape such that only the concave regions of the object are smooth while maintaining exactly all the convex regions. Now, this might seem a bit niche. It's actually much more formalized mathematically. And this was one of my first projects that I worked on. So it has a very special place in my heart. It's not just interesting mathematically, which, now come to think about it, might be enough for this crowd, but the way we solved it to a computer graphics audience is you might want this to simulate how rust accumulates on an object. So if you think about how rust or dirt accumulates, it will only accumulate on concave regions, not on convex regions. So that's where you would want a concave only smoothing. You may also use it as a way of simplifying shapes in a way that strictly contains them, so that you can use them in fields like animation for collision detection. If you've played a video game where you've used something called a hitbox, where like you're shooting at someone and you don't hit them, but the game thinks that you hit them, that's because it's using a cage around the object to compute collisions. We can use this method to compute such cage. So anyway, that's another fundamental geometric problem, right? The input was a geometry, a shape, and the output was a different shape, which came from smoothing the previous shape with geometric methods. So those are two examples of my work on solving fundamental geometric problems. But lately, I've been moving away from those sorts of work and into something that I like to call Geometry Plus. Now, Geometry Plus is not this newest geometry-based subscription service where you have to pay $10 a month to get a new triangle in the mail or anything like that. It's actually much more simpler than that. It's literally a plus. It's adding geometry with other fields, combining them to open the door to new problems and new solutions that are greater than the sum of their parts. So I thought I'd show you some prototypical examples of this. For example, consider this work. This is a work where we bring a new perspective to a classic geometry processing problem from the lens of signal processing. This is a joint work with Noam Eigerman, again, from Adobe, and my advisor, Alex Jacobson. In this work, we got interested in this concept from signal processing called compressed sensing. Basically, it's a way of finding the dominant features of a signal, like an audio signal or an image, such that you can store it using it much less memory space. So where should I sample this signal such that I can know the most about it with the fewest number of samples? So we read about this and we had an idea. What if we treat a surface as a signal that we are compressing? Specifically, what if we compress not the surface itself, but some differential quantity of it? If we do that, we can use the tools from compressed sensing to make the surface piecewise developable, which means that it's easier to fabricate out of sheets of metal, for example. Piecewise developability is a very important question in our field, and we took this concept from a neighboring field of signal processing and brought it over to solve this developability problem. So that's one example of this geometry plus vision that I'm trying to sell to you, where we teamed up with this field of signal processing. Another example is this work that I'm particularly proud of, where we look at existing algorithms from our field from the lens of algorithmic fairness. This is a joint work with Anna Dodick from MIT and Professor Theodore Kim and Amanda Phillips, where we survey the computer graphics research literature, for example, algorithms that generate the geometries of the human body. And we studied how we currently treat gender as an algorithmic variable and the harms and biases that we introduce by doing so. This was a very interesting collaboration that required not only knowing about human parametric modeling and computer graphics, but also teaming up with people from gender studies and algorithmic fairness. Another recent project I've worked on is this one. Here we use geometry to tackle a classic problem from physics simulation, which is how do things break when they receive an impact? This is a joint work with Jack Long, Leticia Matos da Silva, Aravind Ramakrishnan, Yushan Yang, and again, my advisor, Alex Jacobson. And the idea is, you might have heard of this thing called vibration modes. These are an object's most natural ways of deforming or of vibrating. This might be something that you learned in physics in high school or in college. We take this concept and extend it to introduce an object's fracture modes, which are analogously, its most natural ways of breaking. So what are the likeliest ways in which an object can break? Our fracture modes can be pre-computed for a given shape like this spaceship at the design stage, for example, in a video game. So a video game artist designs this object and computes its fracture modes. And then on runtime, since they form an orthonormal space of the orthonormal basis of the space of fractures, they can be used for real-time simulation that is different depending on the nature of the impact. Now, this was a very fun project to work on, mostly because watching things break is very fun. And watching things break in a computer where you don't have to clean up after, it's even more fun, right? One thing I realized while working on this project is that it's also very satisfying to sort of play the GIF backwards and see it go from broken to fully assembled, right? Again, that's something that's easy to do on a computer, right? Because I just play the video backwards. But putting things together in the real world is what this work is about. Right after our work on fracture simulation, we teamed up with our friends Yunchun Chen, Ziyi Wu, and Animesh Garg from our department's robotics group. And we used our fracture simulation from the previous project to construct a massive data set with over 1 million fractured objects, which then can be used as a benchmark for different fracture reassembly algorithms. By the way, I'll mention here that we just had our first follow-up to that work where these authors here actually scanned real-world broken objects, and they show that they can get good results by combining our synthetically generated data with their real-world data. I'm very proud of this follow-up. I would love to talk to those authors, and the results are very impressive, and it shows the power of the combining synthetic with real data. I also wanted to bring this up because we both have pop culture references in the title. I just wanted some validation that ours is clearly a better pop culture reference, right? Theirs seems very far-fetched. Anyway, so that was a tour of what I mean when I say geometry plus. Now I'm going to go more into depth in this project, where we propose reframing a geometric problem as a statistical learning one. And this is a joint work that we just published at the end of last year with my advisor, Alec Jacobson. I'm not putting his face again because that might be too big on the screen. It's just him, but he's involved again. So let's start with a simple question. Consider an oriented point cloud of a surface like this. This is what you get, for example, from a LiDAR scan that's mounted at the top of a self-driving car, right? This is how we usually capture geometry in the real world. We shoot a bunch of lasers, record how they are reflected, and that gives us a bunch of points in space. And usually we can also get their normal direction. So we not only know that there is some surface there, we also know which direction the surface is pointing, right? So that's what an oriented point cloud is. Now imagine that I place an object somewhere in the plane, like a car, right? Here's a question. Does this car intersect the surface described by this point cloud? Before we wrote this paper, the way we would have answered this question, and maybe the way that you would answer it too, is by using a surface reconstruction algorithm to convert this point cloud into a fully determined surface representation and then check if the car intersects with that surface, right? This makes sense. Of course, none of the points are in the car, right? But a point cloud is a discrete representation. We assume that it's representing a continuous surface, so we can't really conclude whether the car intersects the point cloud, the surface represented by the point cloud, without actually reconstructing a complete surface. And the most well-known surface reconstruction algorithm in computer graphics is Poisson surface reconstruction. Basically, Poisson reconstruction uses the point cloud to get a scalar field, something like this, that takes positive values outside the shape and negative values inside the shape. Then the zero level set of this scalar field is the reconstructed surface. Our car does not intersect this reconstructed surface, so thanks to Poisson surface reconstruction, we can at least formulate an answer to the question. According to them, the car does not intersect the surface. Okay, that's one valid answer. But it's a bit of a scary conclusion to reach, right? I want you to think about it with me. If you're the one that's sitting in that car, would you be so sure that you're not going to crash against the surface or against the wall here? Now, just by looking at the point cloud, it is intuitive that there are many shapes that could be the surface, right? Sure, the surface could look exactly like the Poisson reconstruction one. That's a possibility. But it could also look like this, right? It could look like this, or like this. Surface reconstruction is an underdetermined problem. So there's probably an infinite set of possible surfaces, and Poisson reconstruction is only considering one of them. In this work, we propose a way of formalizing this probabilistic view of surface reconstruction in order to give more complete answers to queries like this. It will not just be useful for collision detection, but also for other applications like raycasting, point cloud repair, or next view planning. So we'll achieve this by combining the Poisson reconstruction algorithm with insights from statistical learning theory, specifically the concept of a Gaussian process. So I'm going to go through these one at a time. Usually I give this talk to a graphics audience. So I brush over Poisson reconstruction and explain to them what a Gaussian process is. Today, I'm going to do it a little bit differently and start by telling you about Poisson surface reconstruction. Now, if you've heard of Poisson surface reconstruction, I ask that you now put aside what you think, how you think Poisson surface reconstruction works. I'm going to tell you how I think of it, because there are many interpretations. The input to Poisson surface reconstruction is an oriented point cloud, which mathematically is just a bunch of points and unit vectors. From this point cloud, we start with an interpolation step, which defines a vector field for every point in space. Now, this might seem like a lot of math, but in reality, all that's happening here is a weighted sum of the normal vectors in the point cloud, right? I want to go from a discrete set of vectors to a vector field. It makes sense that what I do is, at each point, I do a weighted sum of all the vectors in the point cloud. The weight of each vector will answer to this kernel function, which is higher the closer x is to pi, which also makes sense, right? If I'm doing an interpolation, it makes sense that I trust the closest vectors more than the ones that are far away. And there's also this term, which is just dividing by the local sampling density, which might not make a lot of sense now, but if you think about it for a bit, it needs to be there. We usually write this in matrix form like this, right? With some transpose vector, diagonal matrix that's inverted, and another vector which just concatenates the vectors, the normal vectors in the point cloud. Okay, once we've defined this vector field, the next step is to solve a partial differential equation. So we find the scalar field whose vector field is the gradient. That's what this is doing, which is effectively a Poisson equation. That's where the method takes its name from, right? But in fact, even if that PDE solve was such a critical part of the method, that's not the part I'm going to care about. The part I care about is this vector field interpolation. Because the punchline of this talk is going to be, and you might be thinking about it already, that we are going to interpret this vector field as the mean of a Gaussian process. And that will allow us to also draw statistical insights from it, not just a single vector for each point in space. So let's do just that. Let's remind ourselves what a Gaussian process is. A Gaussian process is a way of doing supervised learning. We start with some function that we want to know. We formulate a prior on that function, which is given by a mean and a covariance function. Then we observe some data of that function, so some instances of that function at some points, which may or may not have noise. I'm assuming no noise in this simple explanation. And from that observed data and our priors, we get a posterior distribution that tells us for any point, any new point that I haven't sampled, what is the mean and the variance of the distribution at that point. And these answer to simple matrices that I can just multiply. So anyway, there are many Gaussian processes, obviously. Otherwise, there wouldn't be a seminar about them. For many applications, and But basically, most of them look like that. There's a prior, there's an observation, and then there's a posterior distribution that answers to some matrix multiplications. A common simplification that one does in Gaussian processes is assuming that the mean is 0. The effect that this has is it makes this equation here much simpler. So we're going to do that. Of course, this is valid as long as the mean prior is a constant. You can always deviate the function by the Gaussian process by a constant. So this can be done without loss of generality. And if the mean is not a constant, we'll see some examples of that later. So for now, let's assume that we can do this without loss of generality. Now, I didn't know a lot about Gaussian processes when I started working on this project. And if I look at these equations, the only part that scares me is this matrix inversion, right? I did some linear algebra, and I know that inverting a matrix, best case scenario can be costly. Worst case scenario, it can be ill-defined. It can be non-robust if you do it in a computer. There are many things that can go wrong with a matrix inversion, right? So an interesting step for me might be to look at what this matrix looks like. Of course, this matrix is, the size of this matrix is the order of the data. So how many points in the point cloud, which can be a lot, right? Now, you obviously in this audience have seen a covariance matrix before. I hadn't. So to me, I just started looking at what this matrix looked like. Well, it had mostly zeros in every row. Every entry is positive, and the highest value is always in the diagonal. Now, off-diagonal entries that are either 0 or the ones that are non-zero basically just measure how close is a point to each other. So, this would measure how close is the second point in the point cloud to the third point in the point cloud, or the fourth point in the point cloud to the third point in the point cloud. This is what a covariance matrix is, but for me, as someone who had never worked with this before, I thought this looks kind of like what I call a finite element mass matrix. This is something that when we do physics simulation or solve partial differential equations on meshes or even using finite difference grids, this is what the mass matrix looks like. So this is what it looks like if you multiply different basis functions against one another. And in finite elements, we usually try to avoid inverting these matrices because it can be very costly, it can be non-robust. Instead, we use a trick called matrix lumping. Now, this is a part of the talk where when I give it to a graphics audience, no one bats an eye, but I know that some of you are going to cry inside a little bit when I say this. So don't worry, we can talk about the validity of this step later. But what I did in this project was, okay, if this looks like an FEM mass matrix, let's lump it like a FEM mass matrix. Basically, push every value to the diagonal, and our work here is done. This is a diagonal matrix now. So that's what we did. And we can then turn that scary matrix inversion into a diagonal matrix. Ta-da! So you might be thinking, how legit is this covariance matrix lumping? The answer is nuanced. So in the paper, we showed that it's valid under some assumptions. But since then, and this isn't just me pandering in this talk, I've heard that there are much better ways of doing it, using cover trees, for example. And if I were writing the paper now, maybe that's what I would do. So back to where we were, but now with an easier matrix inversion. Now D is just a diagonal matrix with non-zero entries. We know how to invert that, so that's easy. So we're back to our Gaussian process. Now, in this example, we've considered a scalar function, but just like we consider a scalar function, I can consider a vector-valued Gaussian process. This is just a Gaussian process on each coordinate, right? So this makes sense. And that's where I wanted to get. Vector-valued Gaussian process with a zero mean prior and a lumped covariance matrix. And finally, the most critical part of this is that, like I promised, we reach the same equation for the mean of the Gaussian process than the vector field from Poisson surface reconstruction. So this was our main realization, right? Or aha moment. by doing some assumptions in the definition of a Gaussian process, we can recover exactly the same vector field that one defines in Poisson surface reconstruction. This is the main observation in our work. Everything that comes after this is exploiting that observation. So how can we exploit it? Well, we introduced something called stochastic Poisson surface reconstruction, which basically just means let's pretend that Poisson surface reconstruction introduced 20 years ago actually did mean to do a Gaussian process from the start. Let's pretend that Poisson reconstruction was a Gaussian process. What would that look like? Well, our input point cloud now is not just an input point cloud. It would be samples from a distribution, right? Our interpolation step going from these samples to a vector field is no longer just a simple interpolation. It's a Gaussian process with a given prior. Instead of a single vector field, we get a whole vector field posterior, meaning that for any point in space, we don't just get one vector, we get a whole set of possible vectors with different probabilities. Now, earlier we solved a partial differential equation. Earlier we solved it in the space of functions, right? Which is usually the space in which you define a partial differential equation. But we can similarly solve it in the space of distributions to get a posterior distribution for the scalar field from Poisson surface reconstruction. This means that for every point in the plane, we have a mean and a variance, which gives us a fully determined Gaussian distribution of what the scalar field looks like at that point. This distribution, again, is fully determined by the mean and the variance. And as we change the query point, those quantities will change as well, and it will give us a new distribution. Points of the plane that are closer to the data, so closer to the point cloud, as expected, will have smaller variances, which results in more certain values, whereas points that are far away from the data will have large variances, which lead to more uncertain distributions. This is not only mathematically interesting, it also lets us compute important queries about different points in space. So, for example, we may want to compute this integral, which is nothing but the probability of the scalar field being below 0 at this point. But let's remember the problem that we're solving. In Poisson reconstruction, the scalar field was negative inside and positive outside, right? So the probability of the scalar field being below 0 is the same as the probability of a point being inside the shape, which we can plot for every point, and it looks something like this. This is a critical quantity for reconstruction, right? We finally can formalize a little bit of that space of possible reconstructions that we were looking at with the car, right? Now we don't just have one surface, we can quantify for any point in space how likely is it to be in the reconstruction. Now, I'm going to keep showing you simple 2D examples, but of course, when I say geometry, I mostly mean 3D geometry, and we can compute all of these quantities for 3-dimensional point clouds. Something we notice by looking at these probability functions is that it's easy to tell which ones represent shapes which we are more certain about and which ones don't. This is simple, right? If all of the values are either 0 or 1, meaning that for every point in space, I am either sure that it is on the shape or sure that it is outside the shape, then I am very certain of what the shape looks like by definition, right? The more I have points where my probability is close to 0.5, the least certain I am. So inspired by this, we introduced this concept called integrated uncertainty, which just measures how far the probabilities are from 0 and 1. This quantity goes down as you refine the shape. As we sample more and more points from a given shape surface, we become more certain of what the final shape looks like, which makes sense, right? And we think this concept can be useful, for example, as a stopping criterion in scanning. So you can do progressive scans of a shape and wait until the integrated uncertainty is below a threshold amount to be sure that you get surfaces of similar reconstruction quality. Another query we can answer using this quantity is, where does a ray intersect against the surface? Now, given that there's many possible surfaces, the ray collision distances will not just have one value. Instead, they will follow some distribution. In principle, this distribution can seem very hard or impossible to compute. However, we introduce a way of doing this thanks to our probabilities of each point being inside the shape. We can interpret these probabilities as the differential probability of a ray terminating, meaning this scalar field is basically just a marginal probability of will my ray hit something at this point in space, right? Which is basically, would my ray finish here, which is a quantity that we use a lot in computer graphics for things like volume rendering. In a way, I'm looking at this as if I were shooting a ray at a cloud. That's the same kind of model that we use in volume rendering. And it lets us compute something called the transmittance, which is the probability that a ray reaches a point of its trajectory without intersecting. This is a classic trick in volume rendering, and from it, we can sample to get this distribution. And not just in that simple example, so consider this spaceship, and I'm going to simulate a point cloud scan of it. Here I'm doing a point cloud scan with where I'm sampling the left side of the spaceship, the stage left side of the spaceship, much more than the right side. And I'm going to place two hypothetical cameras, one aiming at the left where there's more data, and one aiming at the right where there's more data. I'm going to use exactly the technique I described, and we can see that the spread of the possible ray collision points from the camera that's aiming and the uncertain part of the shape is much wider than for the camera that's aiming at the part we're more certain about, which is what you would expect, right? Why do we care about these queries? Well, in fact, it's a very useful queries that we can combine with the integrated uncertainty that I defined before. So for a given point cloud, we can place many hypothetical cameras around it, and for each camera, simulate many rays and find the points at which they would intersect the surface. Then we can add those points to the Gaussian process, update the Gaussian process, update our integrated uncertainty, and ask how better did our reconstruction become? So how surer are we of the shape now that we have added more points from this camera position? That's a bit of a mouthful, but eventually what this means, it lets us score cameras by how useful they would be as the next scanning position. So we can see that, as expected in this shape that we sampled much more from the back, it would ask us to look at it from the front. So that's just a lot of useful queries that are critical for the reconstruction process that we get just out of that integral, that probability of each point being in the shape. But there are other statistical queries that we can ask. For example, we can compute this other quantity, which is the probability of a point being on the surface. Strictly speaking, it's proportional to the probability of a point being on the surface, right? We don't know the normalization constant, but basically measures how likely is it to be on the surface. And it looks something like this. This quantity is useful in cases where we have an incomplete point cloud of an object, like here, where we can use these probabilities with something like a Metropolis Hastings algorithm to sample new surface points. Okay, so by now you might be thinking, all right, those are cool applications, whatever, but what about the car, right? Does the car hit the surface or not? Well, we need to go one step further to answer that question and compute something called regional probabilities. So for the car isn't just a single point in space for which we can compute its probability. The car is a whole region, and the question we need to ask for that car is, what's its likelihood of intersecting the shape, or rather, what is the likelihood that every point inside this region has a negative scalar field? But fortunately, that's just a multivariate Gaussian that we can sample, a cumulative distribution of a multivariate Gaussian that we know how to compute reliably. And we can use that for collision detection. So finally, we can see the car example. I constructed this very simple scene, simulated a point cloud of it. I moved my car around to know different collision chances. Okay, so you might have heard this saying, and forgive me, it's just I came back from LA today. There's a thing that they say about actors that's like, they do one for the studio, one for them, right? Or one for the studio, one for me, in the sense that they will play in some Avengers movie that they really, really don't like, but that's how they get the money to fund their independent film that they really, really want to do, right? Well, that's kind of what's happening here. All these computer graphics applications, the reconstruction applications, those are the ones I did for the reviewers, right? For the studio. Now I'm going to tell you about the applications that I'm excited about and the reason why I wanted to work on this project. So if you recall, our contribution was showing that Poisson reconstruction could be seen as using a Gaussian process with a specific prior, right? And surely this audience, where you're used to this formulation, you're already thinking, well, can we dare do better than this? Now that we understand it as a prior and not some mathematical formulation from Poisson reconstruction, we understand it as encoding some previous knowledge about the shape. Can we change that prior and do better than Poisson reconstruction? So for example, a known problem with Poisson reconstruction is that it may produce open surfaces. And in the real world, there are no open surfaces, right? Objects are usually closed. Solid objects are usually closed. And in our paper, we show that changing the prior slightly can enforce closed surfaces in the reconstruction. This is a problem that whole papers have been written about, and with our new statistical formulation, we can solve it with one line of code because we understand what these priors are. And this works beyond just 2D simple examples. So for example, in this apple, we simulate a pointless scan of it. Poisson reconstruction produces an open surface, which, by the way, my husband said that this looks like the evil guy in Plants vs. Zombies. So now I can't see anything but that. But anyway, it's an open surface, right? There are no open apples in the real world. So we can add our modified prior to enforce that it is closed. And we also get the variance map that tells us what regions we are more or less certain of, and which regions we're basically just relying on our prior. Even beyond very simple examples, for this car, this is what the Poisson reconstruction output looks like. Here's ours with a very simple geometric prior that's already much better. Now, these are very simple geometric priors, but I think a very exciting avenue for future work may be to use our understanding to incorporate more complex, task-specific learned priors to Poisson surface reconstruction, which I think would be revolutionary. And another maybe more boring avenue for future work, but maybe less lower hanging, is that one can improve our algorithm's runtime. So while computing the mean of our algorithm is very efficient, the variance is very slow. The reason why is because of this part called solve PDE step that I didn't tell you much about. I didn't tell you much about it because it's not very interesting. All we do is we discretize space and solve a bunch of linear systems. Computing the mean of the scalar field amounts to solving one linear system of size m cubed. M is the number of grid points along one dimension, which can be done very efficiently. However, obtaining the variance means solving m cubed systems of size m cubed, which is intractably slow, right? In computer graphics, m6 might as well be infinity. To make this from intractably slow to acceptable, we use a simple trick that's common in computer graphics, which is we use a subspace. So in this case, we take the eigen functions of the Laplacian on a square or a cube and solve the equation projected to that subspace. And that way we can get a solution. And with that trick, we take it from very slow to slow, which is still a little bit disappointing. And you know, I'm happy to spend a lot of computational time if something is very elaborate, but this doesn't seem very elaborate, right? This function seems very easy to approximate. Like, if anything, if you just gave me these two color maps, I would think that the left one is more complex, right? How can it be that we're spending most of our computational time on the right thing? So I think an interesting avenue for future work is to try and make this faster. Now, a question I always get when I talk about this project is, well, couldn't you just do all of this with a neural network instead of a Gaussian process? And honestly, I never know what to answer to that. So I thought, instead of getting it as a question and looking like I don't know what I'm talking about, I'll add it as a future work possibility. And that way I get ahead of it. So anyway, how can we do this with a neural network? I don't know. But I've been looking into these things called Bayesian neural networks, which at least seem to produce variance maps that look sort of like the ones we are outputting. So it might be interesting to go more into depth into what this means. More broadly, in our work, we combined our concept from geometry with Gaussian processes. And something I've been thinking about for the past few months is what other aspects of the geometry processing pipeline can benefit from Gaussian processes. So, here are something that came to mind, like shape interpolation. You go from one shape to another, and you want to find whichever shape is in the middle. There's obviously some uncertainty there, right? Similarly with keyframed animation, so you have a character in one pose and a character in a different, the same character in a different pose, and you want to smoothly interpolate between those two. Or shape completion, where you have a partial view of a shape and you want to reconstruct the rest of it. These are all cases where we're using priors to obtain an output, but we're usually not quantifying the uncertainty of those assumptions. So I think that's also an interesting avenue for future work. More broadly, be it with Gaussian processes or with other techniques from statistical learning, I think a very promising combination is to quantify the uncertainty of the geometry processing pipeline. So this is the vision that I want to pursue in the next few years, which is to integrate uncertainty into the whole geometry processing pipeline. There are some works on this, like ours, but they mostly focus on the capture step. So, how to go from a real world observation to a stochastic captured object. This makes sense since capture is usually the main source of error and uncertainty in our world, but there are many other sources, and I think it's very promising to carry that uncertainty over and do uncertainty aware X, where X is a classic method from geometry processing that may not be related to the capture itself. And hopefully that is not just useful in and of itself, but it can also teach us more about the capturing steps. So we can have a sort of feedback loop where we care about a specific property of an object, we scan it, we do a stochastic aware computation of that property, and that teaches us where or how or if we should keep scanning. Now that vision looks a lot like a pipe dream right now, but I hope that ours can be a first step into making it a reality. And one of the reasons I'm here, and I was glad to get your invitation, is that I'd like to convince all of you to work with me on the further steps to make this a reality. So I figured I would end by reminding you or suggesting a few project ideas that I'm genuinely thinking about. So if you're interested in pursuing, I would love to collaborate on them. So I've told you about some of these. So for example, this has to be easy to compute faster. I don't know how, maybe you do. And faster would mean something that's of the order of the number of points in the point cloud. Linear in the number of points in the point cloud, that would be great. Another is learn task-specific priors. So we already created this whole framework to use Gaussian processes for surface reconstruction. How can we introduce task-specific priors? So for example, what if I wanted to do my algorithm, but I know that everything that I'm going to be reconstructing are cars, right? How can I do better than just the vanilla stochastic Poisson surface reconstruction that I introduced? That seems like something I could do, but maybe I just don't know enough about Gaussian processes, and that's why I'm here. Finally, more Gaussian processes. So I have all these ideas of where Gaussian processes could fit in the geometry processing pipeline. I would love to talk to you all about them. So anyway, these are some ideas. I mean that genuinely, by the way. Like, do reach out if any of those sound interesting. And I've convinced you of this Geometry Plus marketing trick, feel free to find my contact information on that website. And I'll end this talk by thanking all of the amazing people that I've had a chance to work with in the past 3 years. It's really been a wild ride, and thank you all for listening.
So I wanted to say thank you very much, Silvia, for the wonderful talk. We will now move on to the question, answer, and discussion periods, and we're going to have a period of questions that's going to be live streamed. And then after that, we will have a non-live streamed period of questions for any kind of question that somebody might want to ask that they prefer sort of not to have on YouTube later. And so if you have a question for this talk, please feel free to use the raise your hand button or type your question in the chat. So you have a question from Jeff?
Yeah. Hi, Silvia, thanks for the amazing talk. And this is really cool research, and I'm really excited to see Gaussian processes being used in this way. One question I guess I have about this idea of sort of like uncertainty-aware geometry or uncertainty-aware, graphics in general is, I think, thinking about like a lot of the decision-making pipelines where we do use like uncertainty quantification today, like things along the lines of like active learning or Bayesian optimization is, typically we're using this uncertainty in a very sequential way where, we'll say like gather a little bit more data, we'll, use a surrogate model like a Gaussian process to determine where we're uncertain and use that uncertainty in a way to guide where we gather that next data point. But this is like an inherently sequential process. I know very little about, I guess, like the field of computer graphics, but I always kind of get the sense that it's this field where, we're typically doing a lot of things in parallel and not necessarily in a sequential way. And I guess I'm wondering how you see like the uncertainty being used in this field, if that uncertainty can only be used to sort of make sequential decision processes.
Well, that's a great question. I have so much to say. Maybe we can talk more about it. By the way, great to hear your voice for the first time, Jeff. So there are, okay, so maybe like the easiest way to answer this is by broadening maybe your conception about computer graphics. There are many examples where we do use sequential decision making. So for example, the classic example, and the one that especially my advisor always likes to give, is you're scanning a bridge, right, with a 3D scanner, and you want to know whether the bridge will fall off or not, right? Well, you want to scan it from the best possible positions, right? Imagine you're scanning it with a drone. You need, it costs money to move the drone around to take a new scan. It costs time for the scan to happen. So you could have a drone that's moving around. And yes, a lot of the internal things that are happening inside the computer that are going from like the drone output to a point cloud, or even the reconstruction from that point cloud, can be heavily parallelized. But once you have the reconstruction, you have to make the decision of where do I scan next? That's sequential, right? And that's something that is looks a lot like the active learning stuff that you were talking about. And then there has been work in that direction. There's a lot there. That's like the classic application. One I really like to consider lately is there's a lot of, lately computer graphics has been used a lot to generate data sets for machine learning applications. So for example, you may look at all of these computer vision models that say, I was just because I had opened Twitter earlier and I saw, how TikTok is teaching researchers how to recognize different dances, right? And it's basically an algorithm where you put a video of someone dancing and it captures the style and the steps of the dance, and then I think it teaches you how you could dance it. I don't know this specific algorithm, but even if it looks like purely a computer vision thing where like you're looking at an image and labeling different parts of the body and how they move, it's not hard to imagine that probably what happened at the training stage was that someone took computer graphics models of 3D human bodies and moved them in different ways to generate a massive synthetic data set that they trained then a model on to learn to recognize different dances. So that's a benign example, right? But if we're using our generative models to generate synthetic data sets, it feels like a very easy place where uncertainty quantification can fit in saying, no, actually don't add this model because this is just algorithmic garbage that we're not sure about, something that maybe in the traditional computer graphics world, someone would be, seeing it and just discarding it. But we can use uncertainty quantification to automate that and get higher quality data sets, for example.
Yeah, gotcha. Thank you.
So we have another question, I believe, from C.
Yeah, thank you so much, Silvia. This is a really great talk, and I can tell you that you put a lot of effort to putting this together. Yeah, so I noticed that you were talking about the task-specific prior, and I definitely agree that this is a super important problem. And I couldn't help but want to mention one of our work on pre-trained Gaussian processes, which is exactly trying to learn the prior. This might be a little bit of self-advertising. I could be very biased, but we did get very good performance on like robotics tasks as well as like hyperparameter tuning. I think it has like a lot of potentials to learn very task-specific priors by basically learning from other related tasks. So that's like a side note. And I do, yeah.
Do you mind if we start with this and then you can ask, because I'd love to understand where does the prior come in? Like, is the kernel the thing that you're learning, or the mean, or like what do you give me like a high level vision of like what does it work to encode a task specific prior in a Gaussian process?
So it's learning both the mean and kernel, and it's trying to construct a very general search space for both of these functions. So you can like put pretty much any structure with parameters. So think about a neural network as the basis functions, or any structure that an expert that identify could be helpful to construct this GP. And then you learn this all the parameters of this entire system from multitask data. So like using, basically the expert will be the one picking what tasks are relevant. And then you can basically just like optimize it with respect to like some metrics that characterize how close your current task is to, so characterize like your GP, so the GP we're trying to optimize, to the ground truth GP of your current task. And it's like very computationally tractable. So I think that might also benefit the kind of like tasks that you have in mind as well.
For sure. Okay, that seems like to be in the direction that I've been thinking, but obviously I'll look at your paper for all the details, because you probably, even if we agree on the high level, it's useful to see how it's actually implemented. But yeah, that's great. So anyway, I cut you off. You were asking something?
Yeah, so I have some other questions about like relatively smaller aspects. So you mentioned the integrated uncertainty. And when I was looking at it, I was just wondering like whether it's also related to the entropy, and like how exactly that you're picking this particular metric, because I think that's actually really interesting. Oh, Silvia, I think you're muted.
Oh yeah, sorry. God, 3 years of this and still. It should be the entropy. We came up with this before we had read about other works that try to quantify this, sort of general understanding of statistical uncertainty. So it's basically that's basically what it's not the entropy, but it should be the entropy, and they should measure the same thing. And to all intents or purposes, it's basically the same. It's integrating the entropy in a way.
I see. Gotcha. So I have another question that I saw. There's a question in the chat, so I'll hold that.
So the person whose username is S Flores would like me to read the question, so I'm just going to do that. The question says, thanks for the talk. Was symmetry of the shapes considered as task-specific prior?
The answer is no, not because I don't think it's useful. It's definitely very useful for many graphics applications, but I didn't know how to do it. Obviously, there's an immediate, very hard way of doing it, which is very hard in the sense of like hard constraint way of doing it, which is just reduce the space, right? Solve the space in like 1/2 and map it to the other side. But in practice, you know, for example, with like human shapes, what you want is some symmetry prior that you can be convinced otherwise with observations. And I don't know how to encode that in a mean and a variance. I'm happy to be proven otherwise, but I don't know how to do it. If SF Flores, if you have a way of doing it, I'd love to talk to you about it.
Cool. I guess if we don't have any further questions, we can move on to the second part of the sort of question answer period, where we sort of following the end of the live stream. And so before I do that, I just wanted to thank all of our listeners on YouTube for joining us today and for previous seminars. And please check out our website, which is gp-seminar-series.github.io, and sign up to the mailing list there in order to find out about future ones. And thank you so much for listening.